All right, let's get started. All right, please. Doesn't work at all. Okay, it's a great pleasure to introduce a very good friend today. We have Yiwen Chu here today. So Yiwen did her PhD at Harvard under the guidance of Misha Lukin, where she pioneered a lot of very excellent quantum optics research with nitrogen vacancy centers. This is where we crossed paths for the first time. She, after that, in 2014, joined the lab of Rob Schulkopf at Yale as a postdoc, where she did some groundbreaking work on combining quantum circuits, superconducting quantum circuits, with mechanical degrees of freedom. And most importantly, she discovered the true meaning of H-bar. And I'm pretty sure we'll hear more about that today. She took a lot of what she did there with her when she moved in 2019 as an assistant professor to ETH Zürich, where she is now building up her lab and has already quite some really interesting results in the few years that she's been there. And yeah, I'm really excited to see what she's going to be telling us today. So let's welcome Yiwen, and very much looking forward.
All right. Everyone can hear me here and on Zoom? Lovely. All right. Well, thank you, Wolfgang, for the very nice introduction, and thank you all for inviting me here. I've really enjoyed my stay so far and talking to everyone. So today I'll be telling you about some recent work we did in my group at ETH Zurich on creating Schrödinger cat states in a 16 microgram mechanical oscillator. Okay. So let me start by telling you or reminding you a little bit about why Schrödinger cats are interesting, and then I'll tell you more about why we want to create such a state in a mechanical object. Okay. I believe you're all familiar with Schrödinger's famous dot experiment, right? It involves a cat, arguably macroscopic object that get entangled with a microscopic object, a radioactive atom, through this Rube Goldberg mechanism involving a hammer and a poison bottle and things like that. Now, I want to point out that there are sort of two salient points of this dot experiment, right, that make it so interesting. The first, again, is the fact that it involves this object that we perceive as macroscopic, we interact with it in the macroscopic world, but also that in the end it is in some sort of quantum mechanical superposition of two states that we think of as macroscopically distinct, right? Dead and alive. Those are sort of two states of the cat that we think are mutually exclusive in the classical world. Somehow the idea is that what if we could put those states into a quantum superposition? So, so far, this experiment has not been done, and it probably should never be done like this. However, through the years have tried to make states that are somehow analogous to this dot experiment in various different systems, okay, including, for example, the electromagnetic modes of optical and microwave cavities, or using the motional states and internal states of trapped ions and entangling those. Some people would also say that a GHZ state of many spins could be thought of as a quantum superposition of some collective state of many particles, right? A superposition of all the spins up, all the spins down. One can also think of, for example, currents going in two different directions in a SQUID, right? A superposition of those in a flux qubit, or maybe one that is most easy to sort of conceptualize in analogy to the actual Schrödinger cat is atom interferometers, where you take actually atoms or even molecules of hundreds of atoms and put them in some superposition of being in different locations. Okay, so Now, one might ask, right, how do these actually, how close are we to an actual Schrödinger's cat? How does one quantify how macroscopic these Schrödinger cat states are? Well, there are many ways of doing this. It's actually a pretty complicated topic. But one figure of merit that you could look at it as relatively simple one is the mass of the object that is in the quantum superposition, right? And so I've sort of drawn it in this scale here, all the way from zero mass, so photons, right? And then up to, for example, these molecular interferometers composed of hundreds of atoms, which have a mass on the order of 10 to the minus 20 grams. Now, an actual cat, as the internet tells me, is on the order of has a mass on the order of a kilogram, although the internet also tells me that it can be up to 18 kilograms. Between an actual cat and the objects that we have been able to see in a quantum superposition. So what we set out to do is to find something that is intermediate between these systems, right? At least on this one particular figure of merit, the mass. And in order to do that, what we're going to do is we're going to look at so-called solid-state mechanical objects, right? These are, condensed matter systems, right, where we are looking at the collective motion of many, many atoms, many nuclei inside a crystal, for example. And these objects can take many shapes or forms. So I give a few examples here. You can have, for example, so-called phononic crystals, which are just, periodic structures that can confine sound, just like photonic crystals confine light. You can have little membranes or drum heads, right, that vibrate. You can look at, for example, sound waves traveling through a material, right? And they can either travel through the bulk of the material, which are then called bulk acoustic waves, or on the surface of material, like an earthquake, which are called surface acoustic waves. Okay, and the idea, right, is here, this is the collective motion of many, many atoms, and then we can try to reach this intermediate mass regime here that has not been explored in the past. So now, if you look at these mechanical oscillators, the modes of these mechanical objects, right, they're very well described essentially by harmonic oscillators. They're sort of equivalent to a mass on a spring, right? And so it has all the familiar physics that we know from quantum harmonic oscillators. In principle, they can be described in that way. Okay. Now, if you wanted now to talk about a Schrödinger cat state, what could that be, right? Now you can imagine, right, that you take the oscillations of all of these atoms, right, and you look at two out-of-phase oscillations, right? So one of the states is that all of the atoms are, oscillating down, and the other state is all the atoms are oscillating up, which is, just 180 degrees out of phase, right? And one could, for example, call those dead and alive, right? Those two different states, and you can try to put them into a quantum superposition. Okay, but of course this is, not as clear that these are macroscopically distinct states as a cat actually being dead or alive. So how do we define what counts as a macroscopic superposition? Well, so for the purposes of this talk, we're going to use the following definition, right? So if we look at phase space of a harmonic oscillator, so here, phase space is just on the two axes. We have the I and Q quadratures, or the position and momentum, for example, right? And if you look at two classical states of a harmonic oscillator, they would just be points, right? For example, these two red dots here would be two oscillations that are 180 degrees out of phase. Now, of course, in the quantum picture, right, these things are no longer points, but because of the uncertainty principle, so either quantum noise, or if of that, let's say thermal noise or other types of noise, these dots, these points in phase space become some sort of, fuzzy blobs, right? That indicate the sort of uncertainty in phase space of this state. And what we're interested in is creating a state that is a superposition of two of these, blobs, where the noise or the size, the extent of these blobs is larger than the distance between them, so that you can distinguish them at least in phase space. Okay, and that's what we mean by sort of two distinct states of a harmonic oscillator. And now the goal is going to be to try to put them into a quantum superposition. By the way, feel free to interrupt me at any point if you have questions. We don't have little quantum hammers that we can hit our drums with. Most of the tools that we have in the lab are, electromagnetic in nature. So we're going to do, what is done in a speaker classically, right? We're going to take an electrical circuit and we're going to use that to talk to our mechanical resonators, but it's going to be a quantum electrical circuit or a superconducting qubit. So for the purposes of this talk, all you need to know is that a superconducting qubit is a capacitor, so these these lines here, hooked up to a Josephson junction, which for this purpose is just a nonlinear inductor. Okay, so what we have here is a nonlinear LC resonator that we can use as a qubit because it has an anharmonic energy spectrum. So we're going to choose 2 of the states, and that's our qubit. Okay. Now, you can still think of this capacitor as like any capacitor. It has some electric field, these purple arrows here. And what we're going to do is we're going to put our mechanical resonator with a piezoelectric material attached to it in this electric field. All right, so what does piezoelectricity do? Well, it couples a mechanical degree of freedom, right, energy in the mechanical sense, to a electromagnetic degree of freedom. And if you write down the classical sort of energy of interactions between these different objects, right, it would be some overlap integral between, your piezoelectric tensors or wherever this material is, the strain of your mechanical mode, and the electric field of your circuit, in this case, the qubit. Now, if you cast that into a quantum language, what you get is a Hamiltonian that looks like this, right? So essentially what you have is a coupling strength between these 2 objects, right? And then here you have the operators that represent our mechanical degree of freedom, so phonon and our qubit, which are represented by this sigma plus and sigma minus operators here. So sort of a Jaynes-Cummings type of interaction between these 2 objects. Okay, so now let me just briefly tell you what we can do with such an interaction, because these are the tools that we're going to use later to manipulate the state of our mechanical object and also to measure them. All right, so one of the simplest things you can do is with this Jaynes-Cummings interaction, you can allow the 2 systems to just exchange energy in a resonant way. So what you can do is, for example, you can excite your qubit with some pulse of microwaves, right, tune the 2 systems on resonance such that they can exchange energy. So this is, one way to, for example, create a state with a single phonon or mechanical resonator. All right, of course, this works best if you start out in the quantum ground state and you are in the so-called strong coupling regime, where the coupling is much faster than any decoherence rates in your system. Okay, so this is one thing you can do in the sort of resonant regime, right? Another tool that we have is the so-called dispersive regime, where we detune the 2 systems by more than their coupling, right? And in this case, what happens is that effectively the interaction can be written in the following way. And you understand this Hamiltonian in the following way, which is essentially that now the frequency of your qubit, given by the sigma z operator, depends on the number of phonons that you have in your mechanical oscillator, right, which is this A dagger A operator here. And every phonon that you add, the frequency of the qubit shifts by this dispersive shift, which in our case is given by this expression here. Right, so this is exact for those of you who are familiar with, for example, circuit or cavity QED. These are exactly the same types of interactions that one has there. And now, in addition, if you are in this so-called strong dispersive regime, where this frequency shift is, again, larger than the line widths of both the qubit and the mechanical mode, you can use the frequency of the qubit essentially to count how many phonons you have in your system just by essentially measuring its frequency. So these are the tools that we're going to use later on to create and to measure our Schrödinger cat states. Before I talk about that, let me just show you some examples of what these sort of devices look like in real life. So here are some examples, starting from sort of the smallest scales. So this is a picture from a phononic crystal resonator coupled to a superconducting qubit. You see this sort of periodic structure with these aluminum electrodes on top of them. You can also do this, as I mentioned before, with, for example, vibrating drumhead membranes coupled to Josephson junctions. We can also do this with surface acoustic waves. And then finally, what we're going to talk about today are these so-called bulk acoustic wave resonators. Okay, so I'll tell you what you're looking at in this very colorful picture here. So here is a sort of cartoon of our physical device. Okay, it's made up of two parts. The top one is our mechanical resonator, and it's formed by essentially this top surface of this crystal, and on the bottom we have our piezoelectric material, which is aluminum nitride. Now, in addition, we have shaped this material into this dome shape, right? And now you can imagine that just like an optical Fabry-Perot cavity, what we have is a stable Fabry-Perot cavity for sound that is formed by the top and bottom surfaces of this crystal. Okay, and this is the so-called H-bar, high overtone bulk acoustic wave resonator, which are classical devices that are very commonly used, like for example quartz resonators in your cell phone and things like that. So we're going to take one of these things and we're going to put it on top of another piece of sapphire on which we have made a superconducting qubit. So that's this dark gray feature here that you see, right? So in the middle, this X again represents the Josephson junction, and then on either side you have these capacitor pads, and one of them has this sort of antenna that sticks out, and you should imagine that the electric field goes from this antenna all the way over to the other capacitor pads, and along the way it encounters this piezoelectric material, which does exactly this coupling to the mechanical mode that I talked to you about earlier. Sorry. This is what it looks like. Now in real life, it looks like this. This is an actual microscope image, sort of looking from the bottom up through this stack. So this white shape that you see here in the middle, along with this small circle, is the qubit. And then all these colorful rings around it come from the interference of the light from these curved surfaces. All right, and then we take this whole thing, we put it in a microwave cavity that we use for controlling and reading out our superconducting qubits using sort of standard circuit QED techniques. It's basically just a box of aluminum. Here you see half of this box, and you see the little, this entire device inside of it. And then this whole thing goes in the bottom of a dilution refrigerator. Now, what I haven't mentioned is that our qubits and our mechanical modes have frequencies in the few gigahertz regime. So if we cool this whole thing down to dilution refrigerator to millikelvin temperatures, everything should start out in the quantum ground state, okay, which is a good place. Uh-huh. Is this exactly these two chips that are? Yeah. Like levitate on top of each other, but of course actually at the edges we have little spacers that we just put on top of each other, and then we also have little drops of glue that kind of stick them together. So if there are no other questions, I will continue with so now let's look at how these cats are actually generated. Now, some of you might be familiar with different ways that Schrödinger cat states have been made. So there are many protocols out there. What we're using is actually quite an old protocol that was used in these papers here, in, for example, the group of Serge Haroche, to make cat states in microwave resonators using atoms. Okay, we're going to use a similar type of interaction. Okay, and I will try to give you sort of physical intuition for how this protocol works. And the way we'll do that is let's start out with this particular initial state of our joint qubit mechanics system. Okay, so plus and minus here are the two different superpositions of the ground and excited states of our qubit as defined here with these two different phases. And then our mechanical resonator is going to start out in a coherent state, denoted by this complex amplitude alpha here. Okay, so if we take our Jaynes-Cummings Hamiltonian, the one that I showed you earlier, and let's look at like a semi-classical approximation of this Hamiltonian, right? If we put our mechanical resonator in a large coherent state, many phonons, right, then we can approximate this Hamiltonian as the following, right? We can essentially, so if we assume, let's say this alpha is real, we can sort of pull it out and replace our ANA dagger with this complex amplitude alpha, okay? And now you see that Hamiltonian, right, is just proportional to sigma x, which means that these plus and minus which are the x eigenstates of your qubit, are just eigenstates of this Hamiltonian. All right? So essentially what we're saying is that to 0th order in this small parameter here, right? So the small parameter is the number of phonons, so n here, right? Minus essentially the average number of phonons in a coherent state, divided by, again, the average number of phonons. So, for a Poisson distribution, which is, coherent state, right? Essentially, the variance of the distribution divided by the mean decreases as you increase the mean, right? So this number gets smaller and smaller if you increase alpha, right? So to 0th order in this small parameter, nothing much happens, right? The state is an eigenstate and you just get some phase. Okay, it turns out that to 1st order in this small parameter, this is how the state evolves. Okay, it looks a little complicated, but actually here's how you can see this, right? So if you just look at what happens to the qubit, first of all, right? You start out on these 2 different points on the equator of your block sphere. And all this expression says is that over time, they're going to sort of rotate along the equator toward each other. At the same right, your resonator starts out, let's say, with this this coherent state here, alpha, right? This point here is alpha. And over time, depending on the state of your qubit, that coherent state in phase space is going to move in opposite directions. It's going to rotate around the origin in opposite directions. And which direction it rotates in is going to depend on which of these 2 qubit states you started with. Okay, so this is sort of, to 1st order, what happens to the state. Okay, so now I'll show you a actual simulation of the whole system, including this whole interaction to all orders, of course. And just to set this up, what you will see is what I just described. So if you start out in the qubit in the initial state minus, right, so we start out with a coherent state. So this is a plot in phase space. This is a Wigner function for those of you who know what that is. If not, I'll tell you what it is in just a second. But the idea is that it's just sort of a distribution in phase space that tells you, the mechanical state. Okay, so first you see a blob, which represents our initial state alpha, right, for all 3 cases. And the 3rd case we're going to look at is a superposition of these 2 x eigenstates of your qubit, right, which is just, let's say, the excited state of the qubit. Okay? And so what I'm going to do is I'm going to evolve in time, and what you see is what I just described for the most part, right? The coherent state starts to move in opposite directions depending on the state of the qubit, right? And in the case where we started out in a superposition of plus and minus, the mechanical state actually also evolves into a superposition. And this is exactly the sort of superposition of coherent states that I talked about earlier, and what I defined as a Schrödinger cat state for a harmonic oscillator. And the quantum coherence is represented by these alternating positive and negative fringes that you see in between these 2 blobs. Now you also see that they're no longer perfect circles, right? They get kind of smooshed out into these tadpole shaped, and that's of course due to the higher order corrections to the simple picture that I showed you on the previous page. And at this particular time, right, you see that what we form is this sort of Schrödinger cat state, which is a superposition of these 2 blobs that are separated in phase space. And then you can let this continue to evolve, and eventually everything sort of ends up on the opposite side of the origin of phase space. And what I should point out here, right, is at a particular time, like here, for example, where we say that this cat state is formed, actually the qubit state, right, has sort of evolved along the equator so that it actually becomes, both states sort of converge at this point here, while the resonator states have moved maximally far apart in phase space. So the 2 are actually disentangled at that point. Okay, at that point, go with the mechanical state. The qubit state is in a definite state, I think plus y here, for example, and the resonator is in the Schrödinger cat state. Okay, now we're going to set out to measure all of this, all right, and confirm that it actually works. Oops. So this is what we do. Here is our sort of standard measurement sequence. What we do is first we drive our mechanical resonator, or we drive our phonons with a coherent drive to put it into a coherent state with some amplitude alpha. Okay. Turns out actually this drive also off-resonantly excites our qubit a little bit, so we reset it actually by swapping its energy on resonance with another phonon, but it's not so important. But anyway, at this point, your qubit starts out in the ground state. So now we put in a microwave pulse to control the state of our qubit. Let's say, for example, preparing it in the excited state, as shown up here. Then we put them on resonance and we let the two undergo this interaction that I just described under this Jaynes-Cummings interaction. And then we measure. Okay, so what do we measure? Well, one thing we can measure first is we can measure the qubit, okay? And what we do here is essentially we do full state tomography on our two-level system, on our qubits, and we extract, for example, the population in the excited state, which is this green curve that you see here, right? And also the purity of the state. And what you see is that both of them actually start out high, right, around 1. And then what happens, for example, to the purity is that it rapidly oscillates and decreases, which you would expect because it becomes entangled with the mechanical mode. But after some time, this time that I said earlier, when the cat would appear, this purity actually goes up again. Right? It should go all the way to 1 because I said that the two systems disentangle, but because there's decoherence in our actual experiment, it doesn't go all the way up to 1. So now let's see what happens. Instead of measuring the qubit, let's measure the mechanical mode. Let's measure our harmonic oscillator. Okay, and what we're going to do is we're going to measure the Wigner function, these pictures that I was showing you earlier. And we can do that because the Wigner function can be expressed in this following way. It's essentially a displaced parity measurement of our harmonic oscillator. What does that mean? You take your state, you displace it by some complex amplitude, here given by beta in phase space, and then you measure the parity operator. Parity operator is you take all of the population in the even number Fock states, and you subtract all the population in the odd number Fock states. Okay, we can do that because, as I said earlier, we can count how many phonons there are in our system using the dispersive interaction of our qubit. Yes, there's a question. That's a really good question. Yeah, so we drive it by putting the qubit detuned from our phonons, and then we just apply a microwave drive at the phonon frequency. And because the phonons are still slightly hybridized with our qubit, we effectively do a drive on the phonons. Probably some direct driving of the piezo through the piezoelectric material, but we think that the dominant mechanism is actually it has a slight hybridization with the qubit. So effectively, if you're driving the qubit but off resonant from the actual qubit, so instead you're driving the phonon. Yeah, very good question. Okay, armed with all these tools, right? What we can do is we can measure the Wigner function, this fingerprint of our quantum state in phase space. And here is what we see. So at the beginning, as you would expect, what you see is just one circular blob displaced from the origin, which we can choose, right, depending on how hard we drive. That's our coherent state. Now, if we wait this time, which we call the cat time, TC here, right, we see that now if we look at the Wigner function, indeed it has evolved into these two blobs that are well separated in phase space with these interference fringes in between, and then if we wait longer, everything sort of reconverges on the other side. All right. Okay. So now we can explore these states a little bit more. For example, we can change the amplitude of our initial displacement drive, right? Essentially, how far away this initial coherent state is from the origin, and we can control essentially the size of the superposition, the size of the cat. Okay, so here this A is just some arbitrary amplitude that we set in our arbitrary waveform generator, and then this basically changes how separated these two blobs are when the cat is essentially generated. All right, we can also, the Wigner function contains all of the information about your quantum state. So what we can do is this is essentially doing full quantum state tomography of your mechanical mode. All right, and then we can from this basically extract, let's say, the quantum state, the density matrix, whatever you'd like, and compare it to some other, some other states that are interesting. So for example, one of them is an actual superposition of two coherent states, right? I said earlier that, these blobs here are not perfectly round. They're not coherent states anymore. But we can sort of compare it to such a superposition of two coherent states here and here, right? Which is indicated by these crosses. And from that, get a sense of what is the size of our cat, right? And what is the fidelity to that particular state, okay? And then we can also, for example, compare it to a simulation of our full Hamiltonian. So basically what it is that we would expect to get in the end, taking into account the actual process. Okay, and here in this plot, I'm showing you essentially using these two metrics, the size of the cat, which is essentially telling you the distance between these two blobs in phase space, right? I think it's half that distance essentially. Okay. And then the numbers here tell you about the fidelities to each of those states. Yes, sir.
Question?
Sorry, there's a question from the audience, but I'll get to you one at a time. Yes, all right, go ahead. It's very small. It is less than the size of an atom. Yeah, I will summarize all these interesting parameters in a few slides from now. Yes. I think there's another question from the audience here. Yes.
Yes. On what basis can you assume superposition of individual particles or phonons or whatever you're assuming, rather than a distribution of initial states among multiple particles?
Okay, so if I understand your question correctly, right? So here we are looking at a very particular mode of the motion of this collection of atoms in the crystal. Okay, so I'm not claiming that, that's the only thing these atoms are doing. Of course, there are other modes. They might be thermally excited, and as a result, all the individual atoms are undergoing all kinds of motion. But if we look at this one particular mode, which is this, collective motion of the atoms in a very specific pattern, let's say, right? There we're probing only that particular mode of motion, and we see here, right, through these interference fringes, that what we have is a quantum superposition of these, two something like coherent states of this particular mode.
But that is among multiple particles, not single part.
Absolutely.
So why is that not a distribution rather than a superposition?
So I'm not sure what you mean, but the mode itself, of course, is right. I mean, the mode has some shape in space, and it's in some sense distributed over the different atoms, if that's what you mean, right? I mean, in this mode, each of the atoms are moving by a different amount, let's say, right? But it is a collective motion of all of these atoms. So, right, and within that mode, right, each of these states, right, is a coherent state. It is, classically some harmonic motion of these atoms all together. And then we're putting that into a quantum superposition.
Okay.
Not sure if I answered your question. Maybe we can come back to this at the end. I think there was another question in the audience. Yes.
So when you assume that
So first of all, you don't have to assume alpha is real. That just means that a different state of your qubit becomes the eigenstates, right? So if you assume some other phase for alpha. In general, okay, so exactly, that's only an approximation, right? So as I showed earlier, to 0th order, right, your states are, your plus and minus states are eigenstates, right? But that's no longer the case to first order and to higher orders. Right? And that's exactly what leads to these dynamics, right? As time goes on, the states actually become entangled, right? So, but yeah, that's just the approximation that we were making at the beginning. Are there other questions? let me show you some other cool things we can do with our cats. So the other thing, right, as we've already alluded to, is that essentially what this procedure does is it maps different states of your qubit onto different states of your mechanical resonator. And in fact, we have seen that the plus and minus states, what I called plus and minus earlier, now I'm calling them plus and minus x, right? They map onto essentially coherent states that rotate to different places in your phase space, right? Whereas, let's say the E state, in this case, the plus Z state in block sphere language turns into a Schrödinger cat state, right? But then, of course, all of the other cardinal points of your block sphere also turn into other cat states. They just have different phases for the superposition, right? And that's going to show up visually in your Wigner function as different phases for these fringes that you see, right? These red and blue fringes that you see between the two blobs. Okay, so now we can show that is indeed what happens. So by preparing the initial state of the qubit in different cardinal points of the block sphere, what you see here is that, for example, as you expect, plus and minus x turn into these sort of tadpole shapes, and then these other states along this circle here, sorry, not the equator, the plus and minus y and z states turn to cat states with different phases. And it's easier to see this if I take a cut through the fringes, and you see that indeed, as you go around the circle, right, the phase of these fringes in the middle are pi/2 out of phase with each other. All right. Now, finally, one more thing that we were interested in is what happens to the cat. So what we do is we start out with the cat state we have prepared, and we look at how it evolves over time. And you see that, as one would expect, the quantum features are much more delicate, let's say, than the classical ones, right? You see that these interference fringes, those are the signs of quantum coherence, those disappear much faster than the time it takes for these two blobs, right? The sort of classical features to, go back to the origin for the energy to decay out of the whole system. Okay, and so, we can take a cuts through this and plot it over how long we've waited, and you see again, right, these fringes, the oscillations sort of, eventually disappear. And in fact, the interesting feature here are these blue parts, right? These are the parts of the Wigner function that are negative. Negativity in your Wigner function is one of the signatures of a quantum state instead of a classical one. So one thing that you can calculate is something called the negativity. Basically, you just add up all the negative parts, right, and not the positive parts, which is what this expression here does, right, for the Wigner function. And from that, we can extract a decay constant of the negativity for this slice through the fringes. Okay? And we actually see that, as expected, the negativity decays faster for a larger cat. Right? And this comes back to the original thought experiment, right? I mean, one of the proposals, of course, for why we don't actually ever see a Schrödinger cat state is that, a cat is such a macroscopic complex object that all quantum coherence will just disappear really fast, right? And here we see that effect is that, when we make a larger cat, the coherence disappears faster, all right? Okay, all right, so let me summarize what we have done here. All right, so let's just take this, the largest cat that we have made, right? So and imagine, what are the important parameters of the state, right? So if you calculate the effective mass of this mechanical mode, it's essentially you add up the mass of all the atoms that sort of participate in this particular region of the crystal where the mode is localized, right? That's about 16 micrograms. That is 10 to the 17 atoms. All right, so that's a lot of atoms. If you look at the actual distance in phase space, right? Essentially half of the d here again is half the distance between these two x's here. It's about 1.61. Or if you square that number, that tells you if you shifted this whole Wigner function, so this shape here, so that it's centered on the origin of phase space, that tells you essentially how many phonons, right, or how much energy is actually involved in this state. Okay, so that's another interesting measure. All right, and the point here, right, is that this distance here, evidently, right, is much larger than the size of these uncertainty of these individual blobs. Okay, and that's what we set out to make in the beginning. That's how we defined a Schrödinger's cat state. Now, right, like if you, I mean, this picture is obviously way exaggerated, right? If you think about how separated the atoms are when they're in these two states, it's on the order of 10 to the minus 18 meters, which is smaller than the size of an atom, okay? So that, now, so this is sort of what this cat state is, and let me tell you what it is not. So again, coming back to this question that was asked earlier, right? This picture is also misleading because, again, these atoms are moving in all kinds of other directions by much larger amounts just due to thermal excitations of all the other modes in your mechanical object. Okay, so it doesn't actually look like this at all. This is just an illustration to give you an idea. Okay, so let me just quickly then finish up by telling you what, yes? Yeah. Exactly. So we can measure that, and we can also measure, let's say, the single phonon T1 of our system, and that is about 80 microseconds. Yes, so it is much longer than this. So there's a subtle point here. Actually, you would expect the coherence of the quantum part, the negativity, for example, to decay as in the limit of large alpha as 1 over alpha squared. But here our alphas are not quite large enough for that to hold. Obviously, it shouldn't hold at small alpha, right? So we're sort of in some other intermediate regime, and it's much more complicated to predict what these timescales should be. Yeah, but they are shorter than the energy decay rate. Very good question. Yes.
If you look at the energy decay,
Yeah.
is that kind of match?
Yeah, it does. Yeah, we checked that is the case. Yeah. Mm-hmm.
So I see that
Two blobs here.
yeah, one is darker than the other.
Right.
What is?
Mm-hmm. Yeah, so that has something to do. I mean, we see this also. I think you can see this also in some of this other data here, for example. So this is just due to imperfect preparation of our state, for example, right? Like the qubit and the phonons not being necessarily perfectly on resonance, for example. All of these things will then affect or cause imperfections in the final state. Yeah.
Zero.
Of course, yeah. I mean, of course, the finite, there will always be some, these are coherent states, right? There's always going to be some finite overlap between them. What we're seeing here is, sort of qualitatively, right? I mean, the fact that you can see these interference fringes in between, right? You have to have a large enough separation in order for that to be visible at all, right? And again, our criteria is just that the separation, right, like the middle of those blobs has to be larger than, the extent of those blobs, but, or sort of the width of those blobs. But of course, the tails are still overlapping. Exactly.
One question from Zoom.
How should I? Do you want to just?
Can you hear me?
Yes. Mm-hmm.
Oh, hey, thanks for your nice talk. I have a question about the vibration from the fridge. What's the phonon frequency you have in your work, and is that like totally far away from the fridge vibration, or you need to do some decoupling or damping for your?
Yeah, that's a very reasonable thing to be worried about, but our phonons are at gigahertz frequency, so that is much higher than any mechanical vibrations, let's say, that would be in our dilution refrigerator. And now you could also imagine, right, it's this like flip chip thing, and maybe that can vibrate, but luckily, maybe surprisingly, we have found that is not a problem that we have noticed.
So then should I understand your cat state is actually like, it's actually in a large noise, and all your atoms are moving by the vibration of the fridge, but you can still reach a cat state
Exactly, absolutely. Yeah, that's exactly what I said. So even if it wasn't for the fringe vibrations, if you just think of it like, there are also megahertz, kilohertz, hertz modes of this mechanical object, and all of those are at millikelvin temperatures thermally excited, and so the atoms are going to be moving anyway, right? Even if it wasn't for fringe vibrations. And so absolutely, again, we are only measuring a cat state in this particular mode of motion of all of these atoms. But they, you should imagine that they are, doing all kinds of other things at the same time.
I see. They're decoupled, so.
Exactly, they're orthogonal modes. So yeah.
Thanks.
I'm almost just 2 conclusion slides.
Okay.
Yes, and then I'm done.
Maybe do that and defer the questions.
Conclude very quickly. So what are cat states good for? What do we want to, why is this interesting? Of course, probably maybe some of you already know that there are all these ideas of using harmonic oscillators to store and error correct quantum information, right? And in principle, that's a mechanical resonator is perfectly good harmonic oscillator mode. Now, what's special about it? Well, mechanical modes are, let's say, sound, right? Is much slower than light, which means that you can confine mechanical modes to a much smaller volume. They can be much more compact and have lower crosstalk as a result compared to, let's say, an electromagnetic mode at the same frequency, right? So for example, a microwave resonator. So one of the things we're thinking of now is using these special features, these unique features of mechanical resonators for example, storing and processing quantum information. Now, of course, the other interesting thing to do is the thing that I motivated this whole talk with, is to use these states to further, explore these questions of fundamental physics, or using them to, for example, sense, various different things like, either, let's say, there are these theories that propose that we need to modify quantum mechanics in order to explain this transition from the microscopic quantum world to the classical one, right? And explain, why we can't actually have a Schrödinger's cat, right? And these sorts of experiments might actually allow us to probe whether or not those theories are valid, okay? Now, the other conclusion slide that I had was to just quickly tell you about, this is one of the things we're doing in my group in ETH. We're also looking at using these mechanical resonators, the very same ones, for other purposes, like, for example, transducing quantum information between microwaves and infrared light. I actually already mentioned using these systems for quantum information processing. So we're looking at, for example, engineering interactions between different mechanical modes and doing, for example, quantum gates between them. And we very recently started an effort to also couple these mechanical modes to other types of degrees of freedom. For example, spins, defect centers, for example, in different materials, which of course also feel a strain in the material that they're embedded in. All right, so we're doing, these are the people who are doing it. It's a picture of my group, pointing out especially the people that worked on this particular project. So it's 3 PhD students and a postdoc who were involved, and some of our collaborators also who are growing us new materials for mechanical resonators and piezoelectric transducers. All right, happy to answer more questions. Okay, let me take maybe questions from the audience first and then on Zoom. Yeah, go ahead.
Yeah, actually, I read a lot of your previous papers.
Oh.
For the resonator and change the geometry of the resonator to the animal convex.
That's right.
Geometry.
Yeah.
And I was wondering further method, especially for mechanical resonator.
Yeah.
And increase, for example, the size.
Okay, yeah, no, very good. That's a really good question. So maybe let me start with your last question. So right now, actually, our ability to make cats, larger cats, and measure them is limited by our qubit, which has a much lower lifetime, actually only about 10 microseconds, compared to a mechanical resonator. Right? So for this resonant interaction, that, of course, So that's one of the things that we are also trying to improve. We think probably the qubit lifetime is limited by radiating phonons into other mechanical modes, actually. Now, to answer your question about how to improve, or what we're doing to improve our mechanical resonators, what we're doing is we are, so there are many possibilities for what's limiting it, right? It could be surface defects due to the fabrication. It could be the material. We actually have a strong suspicion that the piezoelectric material, the aluminum nitride, has quite a bit of loss due to, for example, two-level systems like resonant absorbers. And we know this because this is very recent results. I don't want to claim too much about it, but basically we see that there's a large variation between the Qs of different harmonics of this Fabry-Perot cavity, and which are at different frequencies, of course. So we're trying out different materials, different ways of growing the piezoelectric materials to try to see if it improves things. Okay, let me think about this. Yeah, okay, I don't know the number specifically for the error. I mean, it depends on also what Fock state you're counting, right? Because essentially this counting process takes some time, and the state decays during that process, so it depends on what number phonon state you are counting, right? The higher you go, the more error there is in principle. But I can say that a large part of, for example, the infidelity in these states, right, is also it's also due to the measurement. So we do normalize out some readout errors, like for example, the readout infidelity of the qubit itself, right, and also some aspects of the fact that it takes some time to do this parity measurement, but definitely plays a significant role in these errors that you're seeing. Yeah. Yeah, I guess I didn't put those numbers on here, but the coupling rate itself is about, for this particular device, it was about 250 kilohertz. Of course, you have to compare that to the lifetimes, right? Which are, it's about 20 kilohertz for the qubits and 2 kilohertz for the mechanics. Actually, yeah, so we have been able to get higher couplings, but there's a trade-off. So what I just mentioned earlier, that the loss for the qubit might be actually limited by radiation to other phonon modes. So if you increase the coupling, it also increases the coupling to all of those modes. And so actually we see that our qubit lifetimes decrease as well. So this was sort of a happy medium that we found for now until we can solve that problem in a different way.
Typically, in these
yeah, really good question. All right, so this is what I was mentioning earlier about how in the mechanical resonator you can have much smaller mode volumes, which translates to having much smaller spacings between modes and frequency. So the free spectral range of our acoustic Fabry-Perot resonator is about 13 megahertz. Yeah. Maybe let me take some questions from Zoom. Okay. Go ahead, Gustav.
Okay, yeah, very interesting stuff. I was curious if you considered implementing echoed conditional displacement gates, and whether there are some advantages to the protocol you're using compared to that. I would say that this is, if I understand correctly, this is kind of similar to, this like state-dependent force that people use in trapped ions, right? It's a similar idea that depending on the state of your qubit, your mechanical resonator kind of moves in different directions in phase space. So I'm not sure if that's what you mean, but you can kind of think of it that way. Yeah, it's a way to do universal control with weak dispersive coupling. Okay,
so I should mention, right, that there are many like other protocols, right, that have been used in cavity and circuit QED especially for making cat states, which allow you to make, let's say, actual superpositions of coherent states. Again, I'm not sure if this is what you mean, but right now we are limited in which of those protocols we can actually implement, because we're far enough in the strong dispersive regime to do measurements, these like parity measurements. We're not quite far enough to be able to actually use the dispersive cat generation protocols that are typically used, but maybe that's not what you mean, because you said it's in the weak dispersive.
Yeah, this is like from last fall, like what they do with the Devoray's group with
I see. Okay.
to generate the GKP states, even though the coupling is interaction strength very small, and they displace the resonator to a high displacement and use that as a kind of lever.
Yeah, exactly. No, that's a really interesting point. I don't think we've put in the numbers to see what would happen there. Again, like, you know, I think we're still in a very different regime, right? From even that circuit QED system, I would say that, you know, compared to the, like, you know, essentially the ratio of our lifetimes to our interaction strength, like the native interaction strength is much weaker. Yeah, I would have to put in the numbers to see what we can do in that case. But yeah, that's a really interesting idea.
I have a question. I see that your beta for each cat is about absolute value of 1. Does that mean that the average phonon numbers in each cat is 1?
Right, so this was sort of this number that I quoted here, this d squared, which is the distance squared, which tells you something about the distance in terms of phonon numbers. And so for the largest cat that we have, it's about 2.6.
That's phonons.
Sorry?
That's the number of phonons, 2.6 in the number of phonons.
Exactly, yeah.